touch here is like introducing the Pope to the College of Cardinals.
What I call the integrate, analytical, experimental, analytical investigation or research. I thought that it would be better to really dedicate not just the early time of the earthquake engineering that meant after the 1906 earthquake in San Francisco, and devote the time to the things that start Helmut in this period here. This is a period that I consider was the start of the brilliant career as a researcher that he continued to from 73 for 35 years, I think, here in this prestigious University of Stanford. Therefore, I changed the name. I must apologize for some of the photos and sketches that have world history and all the world, but I would like to really devote most of my time even what he started doing, and then we sent him some really, well, I present the first thing, and suddenly I introduce this introductory remark. It is well recognized that really what was called earthquake engineering in 1949 was not very well defined. Until 1973 was no definition of what really earthquake engineering is called. It was a confusion between engineering seismology that was until 1949 called engineering geology. In other words, the same, but the question was the problem of the development of what we call the earthquake resistant design and earthquake resistant construction, in other words. And that can be called what I refer to is the modern scientific earthquake start immediately after the 1906. The earthquake resistant design and construction didn't start practically after the Second World War. 1933 is considered by the real modern, I think that the start more or less at the end of the 58 and then in the 60 and 70 practically. I present this slide because I like to talk about the question what happened at the end of the 58, 50 and initial 60. The question of steel. Rainforest concrete really started in 50, 60s, 56, 58, working in the application of inelastic plastic theory to the design of reinforced concrete, phenomenal steel for the multi in the United States. But during the Second World War, already was a tremendous advance. Ironically, was developed in many good sense, scientifically and experimentally, during and after the war. And Lehigh was the leading university in testing steel. They have a very comprehensive research program, leaded first by Johnson and then by Vitelmo. time, the question was that the reinforced concrete started using them, promoting the use of plastic theory of unit design for reinforced concrete for multi-story building at 50 already. 58, Bloom, Newmark and all these, and they still want to really compete, and therefore they started. But the problem was what they did, in other words, that they did was all under monotonic and increasing load. Tremendous amount of research. In the 65, they tried to say, well, we can apply perhaps what we obtained for the analysis and design against earth. And this really scared us. Particularly Professor Popov and myself started really working. Just taking only monotonic and increasing. They got frame testing up to failure. Therefore, what happened, we decided in the 60s to make a research program in 3 phases. Starting and including this problem that we have. I have serious problem about the possibility for low cycle fatigue. In MIT, they know it's no problem, but all the tests in MIT was dynamically and for atomic class. 3 milliseconds a pulse. Well, yes, in other words, that's about one second. Earthquake was not 3 millisecond pulse, only one. And particularly in the 1960s, when we have really problem looking the aftershock that occurred in any major event earthquake, we have aftershock. Therefore, there were 2 problems. The possibility of low cycle fatigue and the possibility of incremental collapse. And this was the 2 things that we really worried Professor Popov and myself, and we start this investigation. Let's start first with singles. At that time, we didn't have a big testing dynamic machine. It was working, Professor Pensin, Clark, and all these was working in the design of it that was not inaugurated until 1972. And therefore, even at that, if you have the shaking table, I would prefer to do the quasi-static test for many reasons. I mean, at time I will discuss. But then we will have to do some beams and color, flexible, no influence of shear or biaxial force, to see what can happen. And then go and say, well, this is not realistic, we should go to the connection. How it's connected to the column, in the case of frame structure. And finally, the question about multi-story, you have to have an idea what can happen to the basic subassembly. And this is what really the man that was honored today, Helmut Krawinkler, will do after the first 2 mistakes. Now let's look at when they can be selected to the picture. Let's look at the first one, the picture is very quickly. Well, we got to design a testing frame, and we design a simple testing frame. In other words, you can see a slender, long beam, but using roll shape, no miniature, you have to form in the same that there are many programs. We use these. Let's look at the next one. You can see the size of the same text. Back and forth, back and forth, back and forth. And what we control with this, we decide that the best way